Section 1.3 is real numbers and the number line. I can classify, graph, and compare real numbers, and I can find and estimate square roots. Those are our learning targets for this section and what we're shooting for. Big ideas here. The definition of a square root can be used to find the exact square roots of some non-negative numbers. The square roots of other non-negative numbers can be approximated. Numbers can be classified by their characteristics, and some types of numbers can be represented on the number line. A number A is a square root of a number B if A squared equals B. So for example, 3 squared equals 9. So 3 is a square root of 9. This is our radical symbol, and it indicates a non-negative square root. It's called our principal square root. In order for it to be negative, they would have had to have a negative sign in front. Just like if we see a 2, we know it's positive. Same thing here. If we don't see a sign, it's positive. In order for it to be a negative 2, they have to put the negative in front, and they have to do the same with the square root. The expression under the radical symbol is called the radicand, and together the radical symbol and the radicand form a radical. So here, our radicand is the 7. We have our radical symbol, and this entire thing is a radical. In example 1 here, we're going to be simplifying square root expressions. What is the simplified form of each expression? So, to find the square root of 81, we're looking for what number did we square to get to 81. And if we look at our list of perfect squares here, I have 81 right here. 81 is 9 squared. So, since 9 squared equals 81, the square root of 81 is 9. In B, we have a fraction, so we're going to treat this as two separate things. We're going to find the square root of 9 and the square root of 16. We're going to find the square root of both. Well, 9 is 3 squared, so the square root of 9 is 3. And 16 is 4 squared, so the square root of 16 is 4. Again, remember, A squared equals B, so the square root of B is A. 4 squared equals 16, so the square root of 16 is 4. Now, we're going to find the simplified form of each of the following. The square root of 64, well, if I look at my chart, 64 is 8 squared. 8 squared equals 64, so the square root of 64 is 8. It's kind of like whatever got us to 64. What did we square to get there is our square root. 1 over 36. Well, the square root of 1 is 1, and the square root of 36 is 6. So to get to 1, I take 1 squared. To get to 36, I take 6 squared. So the square root of 1 is 1, and the square root of 36 is 6. Again, we're looking for what number did we square to get to that number. Here I have 81 and 121. So if I look up here, 81, again, is 9 times 9, and 121 is 11 squared. So 11 squared equals 121, so the square root of 121 is 11. They kind of work backwards. They undo each other. So I have 9 for the square root of 81 over, for the square root of 121, I have 11. And again, these are positive because there's no sign in front. When there's no sign in front, we know that that means it's positive. The square of an integer is called a perfect square. When a radicand is not a perfect square, we can estimate the square root of the radicand to the nearest whole number. Okay, so perfect squares are things like when we square 1, we get 1. When we square 2, we get 4. So our perfect squares are the 1, the 4, the 9, the 16 in our chart that we had on the other page. When it's not one of those numbers, we can approximate it. So in example 2 here, it says lobster eyes are made of tiny square regions. Under a microscope, the surface of the eye looks like graph paper. There's a picture of this in the book as well. A scientist measures the area of one of the squares to be 386 square microns. What's the approximate side length of a square to the nearest micron? Well, remember our formula for area of a square is A equals side squared. So to find the side length, we take the square root. We want to know what number was squared to get to our area. And our area is 386. So what number did we square to get to 386? We're looking for the square root. So we're going to estimate it using perfect squares. We're going to go back and look at our little chart here. And we're going to figure out, where does 386 fall in the middle of our perfect squares? 386 goes right about here, right in between 361 and 400. And we're going to figure out which one is it closest to of those perfect squares. Well, here I'm 14 away. Here I'm 25 away. So 386 is closest to 400, which means its square root has to be closest to the square root of 400. 20 squared is how I get to 400, so the square root of 400 is 20, which means the square root of 386 is close to 20, and to the nearest unit will be 20. So here, because it's in between 361 and 400, but it's closer to 400, we're going to take the square root of 400 and get 20. Okay, it's kind of like we rounded because we're using to the nearest micron. We can do this by a calculator as well. If we take the square root of 386 on our calculator, we get approximately 19.65. And to the nearest micron, remember that the 6 rounds up to 20. So we get the same answer here as well. And then remember, to get the square root, you take second key and then your x squared key. And above that x squared, it'll have the little square root sign. Okay, so we can do these estimated by using perfect squares or using a calculator. And we're going to practice without a calculator. So here, go ahead and pause here and give this a try if you'd like. We're looking for the square root of 34 to the nearest integer. So 34 is the number that we're going to compare to our perfect squares. If we look on our list, we have 1, 4, 9, 16, 25, 36. And 34 goes in between 25 and 36. It's closest to 36. And we get to 36 by taking 6 squared. So the square root of 36, okay, the number we square to get to 36 is 6, and 34 is close to that. So we're going to say that the value of this to the nearest integer is approximately 6. Because 34 is closest to 36, so we're going to go based off 36. It's like we rounded before we computed instead of computing and then rounding, which is what we did up here. Up here we figured out what it was and then rounded. Here we're rounding it to the nearest perfect square first and then finding the square root. Numbers can be classified by their characteristics, and some types can be represented on number lines. We can classify numbers using sets. A set is a well-defined collection of objects, such as our specific class. Okay? Each object is called an element of the set. So each student in your algebra class is an element. A subset of a set consists of elements from the given set. So we list those elements of a set within braces. So one example would be of the people in our class. Remember, that's our full set. We want only the boys, or only the people wearing red shirts, or only the people wearing glasses, only the freshmen. Okay, but again, that's from our set, just our class at that time. Okay, and those are subsets. So in order to be in the subset, you have to be in the original set. You have to be in our class in order to be in that second group. And we use braces to list those elements. So curly brackets, again, they don't have to be perfect, but just make sure they're not parentheses and they're not square brackets. A rational number is any number that we can write in the form a over b. So if we can write it as a fraction, remember b can't be 0, we can't divide by 0, then it's a rational number. In decimal form, it either terminates or repeats. Okay, terminates or repeats. So 1.45, for example, is a rational number. 0.6 repeating, rational number, because we could write that as 2 over 3. If you look at the take note on page 18, there's a diagram there where each layer is the same color. So like natural numbers are a lot darker, and that's because they're included in each one of those layers. So natural numbers, those are your counting numbers, the things that naturally we start counting with when we're little kids. 1, 2, 3, 4. That little kids know they don't have any decimals, they don't have fractions, they don't have negatives, not 0. We're just counting at 1 and going from there. Whole numbers are natural numbers, and then we added in 0. Think about it like a hole in your pants or the ground or a piece of paper, okay, like a circle, 0. Whole numbers, just add that in. Integers are natural numbers and their opposites and 0. So it's whole numbers and then the negative versions of the natural numbers. So here we have like -2, -1, 0, 1, and 2. We still don't have any decimals or fractions though. Okay, so keep in mind a number like 2 is a natural number and a whole number and an integer. So we can classify that a lot of different ways, but usually we want the most specific. So 2 most specifically is a natural number, even though it is with these others as well. And then we talked about rational numbers above that are anything that can be written as a fraction or a terminating or repeating decimal. An irrational number cannot be represented as the quotient of two integers. We can't write it as a fraction, and in decimal form, they do not terminate or repeat. Square roots and pi are really good examples here, but some square roots are rational numbers and some are irrational. So if a whole number is not a perfect square, its square root is irrational. What they're saying here is the square root of 9, for example, we know is 3. This is a rational number. It's a natural number. 3 is a natural number. But if we take the square root of 10, which is not a perfect square, we get 3 points, a decimal that doesn't terminate or repeat. That's irrational. Okay, so perfect squares like 1, 4, 9, 16, 25, if we take the square root of those, it's rational, but everything else is irrational. Rational numbers and irrational numbers form the set of real numbers, and that's every number that you've ever dealt with. Example 3 here is classifying real numbers. To which subset of the real numbers does each number belong? Again, we want the most specific one here. So the first thing I'm going to do is check and see if it's rational or irrational. There's no square root, there's no decimal that's continuing on, so this is going to be rational. From there, I break it down a little bit further. Does it have a decimal or a fractional part? No, so it's at least an integer. Is it negative? No, so it's at least a whole number. Is it 0? Nope. So it's going to be a natural number. 15 is a natural number. It's a number that we would naturally start counting and get to. Okay, when we start counting, usually we start with 1, we'd get to 15. In B, check and see, is it rational or irrational? Well, here our decimal terminates. It stops right here, which means it is rational. Now, of rational numbers, we have a lot of subsets here, but we check, does it have a decimal or a fraction? Yes, so anytime there's a decimal or a fraction, we stop at rational numbers. We can't take it down any farther. It can't be an integer, a whole number, or a natural number. It's a rational number. And in C here we check, is it rational or irrational? Well, it's a square root, so we have to be careful. We check, is 57 one of our perfect squares? No, it falls between 49 and 64. So this is not a perfect square, which means it's irrational. If we typed it in our calculator, we'd get a decimal that kept going. And it would look like it stops after a while because that's all that shows on our screen, but that's just because that's the most our screen can show. So if we try these, square root of 9 is 3. 3 is a natural number. In B, we have a fraction. That's a rational number. C, we have a decimal that terminates, so again, it's rational. And in D, we have a square root of not a perfect square. 12 is not a perfect square. So if we type this in, we'd get a decimal that doesn't terminate or repeat. This is irrational. and I'll continue in another video.